Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Ohm's Law. Our objective today is to take a close look at the most fundamental of all electrical relationships, known as Ohm's Law. We'll learn the cause, effect, and opposition relationship between voltage, current, and resistance, and use it to calculate unknown quantities given known or observed inputs. Additionally, we'll use an understanding of Ohm's Law to troubleshoot basic electrical circuits. We are about to delve into one of the most fundamental of electrical relationships, Ohm's Law. An understanding of Ohm's Law is essential for any remaining progression in basic electricity and electronics. I need your undivided attention to this lecture. Pause the lecture often and get involved in the illustrated example problems. Later lectures are predicated upon your understanding of this material, and without which would be utter nonsense. As vital as this topic is, and as important as I'm making it sound, don't stress about it. It's easy. And if my cunning plan has worked, you already know Ohm's Law. You just don't know you know it yet. If you've been following this series in its intended order, you'll recall I've made numerous allusions to this topic using general concepts and non-numerical examples hinting at a relationship between cause, effect, and opposition. All this lecture is going to do is to make some formal statements about Ohm's Law using electrical terminology and throw some numbers into the picture. You can multiply and divide, can't you? If so, you can do Ohm's Law. It's not that hard, and understanding of it opens up volumes of more advanced material. Examining our cause, effect, and opposition relationship, we should be able to predict basic properties given certain situations. If one was to increase the cause, yet opposition was to remain constant, we would expect to observe more effect. By this same token, if we decreased cause, yet opposition was to remain constant, we would be able to observe less effect. Again, using this same relationship, if we kept our cause constant, yet increased opposition, we should observe less effect. Similarly, if we kept our cause constant and decreased opposition, we would expect to observe more effect. This cause, effect, and opposition relationship makes sense and is observable in everyday interactions outside of electrical circuits. Think about school. If you put in a lot of effort and you're in an environment free of learning distractions, you're probably going to get a lot out of school because your cause is high and your opposition is low, yielding a lot of effect. If, however, you slack off a lot and a bunch of quarrelsome raccoons are using your computer as a den, you're probably not going to do well because your cause is low and your opposition high, yielding very little effect. It makes sense. Think in these terms: cause, effect, opposition. No numbers, just think about it. This relationship makes perfect sense. Now take it one step further. Add electrical terminology to our cause, effect, and opposition relationship. What is the cause of charge movement? The cause of charge movement is voltage differential across something in units of volts. Voltage is the cause. What opposes charge movement? Opposition is obviously resistance in units of ohms because an obstacle resists your efforts. Finally, what is the effect of voltage and the property which is being resisted? The effect is moving charges or current in units of amperes. All we've done is we've rewritten our previously easily understood cause, effect, and opposition relationship using electrical terminology, where our effect is current, and current is equal to our cause divided by our opposition, where voltage is our cause and resistance our opposition. Now take it two steps further. Put some numbers in there. If you've got a 12-volt source being opposed by 4 ohms of resistance, you'd expect to observe 12 divided by 4, or 3 amps of current. That's it. That's Ohm's Law. If you can simply remember the cause, effect, and opposition relationship using electrical terminology, and then multiply or divide some numbers, you've got it. It's really that easy. If you're a visual thinker, I've seen a tube and a ball used to demonstrate the first statement of Ohm's Law. This may seem stupid to some of you, but if it works, it is not stupid. The ball represents a quantity of electrons, and how fast it travels through the tube is meant to represent current, where the ampere is the derived unit of 1 coulomb per second. If this ball represents 1 coulomb of electrons, and it took less time to go through the tube, it means more current would be traveling through the tube. If it took more time to go through the tube, it would mean less current would be traveling through our tube. The tube itself represents the resistance of our conductive path. If the inside of the tube is relatively free of obstacles, the resistance is low, being only the friction between the tube and the ball. If, however, I coated the inside of the tube with rubber cement or some other adhesive agent, the resistance of the path would be high. Finally, the slope of the tube with respect to the horizon represents voltage, or differential between the two ends of our conductive tube. If we were to put the ball in the tube and lay the tube flat on the table, the ball would not move. Why? Because there is no incentive to do so. There is no differential between one and the other. There is no voltage difference across. There is no current through. This is true whether the tube is flat on a table, flat on a floor, or laid flat on the top of a skyscraper. Only the differential between the two ends is the cause of current flow through it, regardless of its spatial position to some other agreed upon reference. If, however, I tip one end of the tube up ever so slightly, the ball begins a slow roll from one side to the other. The movement of our quantity of electrons is not particularly rapid because the differential is not that great. If, however, I increase the tilt angle, the ball would travel faster through the tube. More rapid movement of a given quantity of charges was induced by an increase in potential difference between the 2 points. Again, the tilt angle of our tube is the determining factor of the moving ball, not the tube's position relative to a common reference plane like ground. Notice the term I'm using. Ground has nothing to do with it. The right end of the tube could be on the ground, and you lift the other end, or you can keep the left end on the ground and tip the right end down below ground. You could do this same experiment at the bottom of a coal mine or on the top of a mountain. Ground level has nothing to do with it. Although, since we do live on the ground, it does serve as a very handy reference point. If you want, you can increase the opposition of the tube by increasing the friction between the ball and the tube by coating the inside with an adhesive agent. For similar tilt angles, a ball will roll down a high resistive tube slower than a low resistive tube. Are you tracking now, visual learners? I certainly hope so, because we do have to step into math land for a little bit. Let's look at our Ohm's Law relationship and see if we can perform some basic algebraic manipulations with it in case we're ever in a situation necessitating the resolution of different values. Before we begin, let's save some time and use some shorthand to represent the concepts of voltage, resistance, and current. The concept of voltage is often represented by a V, and the units of voltage are volts, also represented by a V. Pending your country of origin, you'll sometimes see the concept of voltage represented by the shorthand notation E, which stands for electromotive force, another synonym for voltage. The units would still be volts. I actually like using both of these shorthand notation schemes to differentiate between a voltage rise, an active source, and a voltage drop, a passive element inside a circuit. We'll return to this concept in a moment. The concept of resistance can be represented by an R, and the units of resistance are in ohms, represented by the omega or ohm symbol. The concept of current is often represented by an I because it was originally named intensity, and the unit of current is the ampere or amp, represented by an A. Quite similar to our energy, power, and time relationship we examined in the energy and power lecture, available at the Big Bad Tech channel, Ohm's Law is a 3-variable relationship, and we can use a pyramid to assist us in our algebraic manipulations. You can use either the concept, the units, or both inside the pyramid relationship to aid us in our manipulations. Use whatever relationship you feel you are most comfortable with using. Our first statement of Ohm's Law is that our effect is equal to the cause divided by opposition, or current is equal to voltage divided by resistance. This is again our original statement of Ohm's Law. You do not need to remember it in this form if you want to use the pyramid relationship. To solve for current, cover it up. Take voltage and divide it by resistance, because voltage is over resistance. This is again our original statement of Ohm's Law. If we are ever given an observed voltage value and a known resistance, we should be able to compute the current through the resistor without measuring it. That's the point. We can use the Ohm's Law relationship to determine unknown quantities using other observations. You're not always given such an easy setup though. What would happen if you could measure the current through a resistor of known magnitude and wanted to solve for voltage? In this case, we'd have to multiply both sides by R in an attempt to isolate voltage, our desired unknown, on one side of the equality. R cancels out on one side, and we're left with voltage equals current times resistance. If doing algebraic manipulations isn't your cup of tea, use the pyramid. To solve for voltage, cover it up. Notice current is next to resistance. Therefore, we need to multiply current times resistance to solve for voltage. Using our original statement of Ohm's law, what if we could observe the voltage and the current and wanted to use these values to solve for an unknown resistance? Using this original statement of Ohm's law, we can invert both sides to get R on top. Then we multiply both sides by voltage, where voltage cancels out on the right-hand side, and we're left with resistance equals voltage divided by current. We could have just as easily used our second manipulation of Ohm's law to solve for R, but then I would not have gotten a chance to wow you with an inverse. Again, if you're looking for a Street Fighter shortcut to this, just whip out your pyramid and start swinging. To solve for resistance, cover it up. One would divide voltage by current because voltage is over current. This simple 3-variable pyramid relationship is very handy, and you'll find yourself using it over and over again for a number of different concepts. Remember this relationship. Think about this relationship. Let this relationship become a part of you. I know this might be a new, weird, and unwieldy concept to you today, but in the upcoming days, weeks, months, and years of use, this is going to become something I expect you to use without a sign of hesitation. It should be a natural reaction and immediately evident that if you decrease resistance and have a high supply voltage, that your current should be high. It should be totally obvious to you if you are supplying high voltage and observing a very small amount of current, the resistance must be incredibly high. And it should be readily apparent if you're observing very little current and a very small resistor, the voltage drop across it will also be exceptionally low. Again, these conclusions and any others you may draw from the different permutations available from this 3-variable relationship can be made without numbers. If your numbers don't agree with the basic Ohm's law relationship, you're doing it wrong, and you need to perform a tactical retreat and reassess your data. The math behind Ohm's law should be easy and the least of your concerns. It's just multiplication and division. Oftentimes, though, it is not the electrical concepts nor the math that hinder the progression of some students, but rather numerical literacy that trips them up. Electrical concepts and math aside, the results will be meaningless if you cannot understand numbers, engineering prefixes, and the units commonly used in technical environments. At some point, you need to come to the very clear and very certain understanding that some numbers are bigger or smaller than others. A millivolt is 1,000 times smaller than a volt, and a kilovolt is 1,000 times larger than a volt, and that same kilovolt is 1,000,000 times larger than a millivolt. Engineering prefixes simply make it easier to write and read unusually large or small values. Before we attempt some illustrated example problems of Ohm's law, we need to discuss 3 topics, namely the difference between a voltage rise and a voltage drop, and we've got to introduce both polarity markers and subscript notation. These topics might seem a little unnecessary at this point, and even glaringly obvious given such simple circuits. But trust me, this brief orientation to rises versus drops, polarity markers, and subscript notations will make life much easier as we progress into more complicated circuits. It's hard to talk about these 3 topics independently without bringing all of them into play at once. So we're going to kind of talk about them all together. You might find it necessary to rewind once or twice if you don't get this section the first time. A voltage source is obviously a voltage rise, and via the passive sign convention, conventional current leaves the positive terminal of an active source and returns to the negative terminal. If you hook a passive element across a voltage source, what goes up must come down. The polarity markers for a passive element indicate that conventional current enters the positive and leaves the negative. What goes up must come down. In our tube analogy, the rise was from the ground to the elevated portion of the tube. The drop was from the elevated portion of the tube to the ground. The voltage source is just like grabbing handful after handful of conventional current electrons from the ground, actively lifting them up, and passively letting them slide down the tube. Again, I often use the shorthand notation E to designate a voltage rise, and V to indicate a voltage drop. In this case, our single element will have a voltage drop equal in magnitude to that supplied by our source. With only one element in a complete circuit, it may seem painfully obvious that every voltage rise is accompanied by an equal and opposite voltage drop. We'll return to a more thorough analysis of this when we cover Kirchhoff's voltage law in series DC circuits. It seems simple and inconsequential, but it isn't, and Kirchhoff's voltage law serves as an extremely powerful and often misunderstood means of circuit analysis. Consider the following 4 example scenarios in which polarity markers are indicated, as well as the direction of conventional current. Pause the lecture and consider each scenario and try to determine if this is an active source, or a voltage rise, or a passive element, meaning a voltage drop. Our first example has conventional current entering our device's positive terminal, and if it enters the positive terminal, it would leave the negative terminal. Therefore, that would be a voltage drop across a passive element. Our second scenario has 2 amps of conventional current leaving the positive terminal. Therefore, this element is an active rise. Consider just these 2 scenarios and link this with our very basic understanding of electrical power, where power in must be equal to power out. In the case of the drop, conventional current is coming into the device, and the voltage drop is across it. In the case of the rise, conventional current is leaving the device because of the voltage rise induced by that source. We could call our rise our supply, and it could be said that our drop dissipates the same supply. It can be said that the source also generates and our passive element absorbs. All these things really just boil down to in and out. Use whichever terms you're more comfortable with. Okay, moving on. Let's check out our third example. In this case, this is also a voltage drop. In this case, 2 amps of conventional current is leaving our negative terminal, which implies 2 amps had to enter our positive terminal. The last one's a little tricky here. In this case, it says negative 2 amps is leaving our negative terminal. What this really means is that 2 amps is entering our negative terminal. If 2 amps is entering our negative terminal, obviously 2 amps is leaving our positive terminal. This would be considered a voltage rise. This last scenario is a little tricky simply because of the negative sign. If you've got a magnitude with a negative sign in front of it and an indicated direction, all it means is that that same positive magnitude is traveling in the other direction. This is a little confusing, but what I'll draw is 4 more examples, all indicating the same quantity. If 2 amps enters our positive terminal, it also means 2 amps leaves our negative terminal. I could also say that negative 2 amps is leaving my positive terminal, or that negative 2 amps is entering my negative terminal. All 4 scenarios are saying the same thing. If that last discussion about current didn't confuse you, let's see if I can do so discussing voltage measurements. If I measured voltage across our element with a reference lead on the downstream side of conventional current, or the negative terminal, I would see a voltage differential equal to our voltage rise. This is again probably self-evident with just one element in our circuit, because there is only 2 nodes in this circuit, and voltage is a 2-point measurement. The 2 voltmeters are in effect reading the same voltages because they are reading voltage at the same 2 nodes. What goes up must come down. Keeping track of the polarity of voltage rises and drops for circuits with multiple elements and even multiple sources will become exceedingly important in the future. Right now, I just want you to realize that the voltage measurement utilized in Ohm's law need not be limited to the voltage rise, but can also be the voltage drop exhibited by an element. For example, an element could be supplied by a source with inaccessible terminals, or is just one of many elements in a complicated circuit. Regardless, Ohm's law holds true. If there is a 12-volt rise supplying a 4-ohm resistor, current is equal to voltage divided by resistance, or 12 divided by 4, or 3 amps. Similarly, if there is a 12-volt drop across a 4-ohm resistor, current is equal to voltage divided by resistance, or 12 divided by 4, for a total of 3 amps of current through it. This is true for any 4-ohm resistor with 12 volts across it, whether it's by itself, in a series circuit, in a parallel circuit, or part of a series parallel circuit. We'll get to these other considerations later. Right now, we're only considering a single element. Again, to refresh, a plus to minus when traveling in the direction of conventional current is a drop, whereas a minus to plus when traveling in the direction of conventional current is a rise. When measuring voltage drops across elements, a voltmeter is customarily employed such that the reference lead is on the negative polarity marker, or the downstream end of conventional current, and the high lead is on the positive polarity marker, or the upstream end of conventional current. If you were to swap your reference lead, it would still indicate the same magnitude, but because the reference is employed on the upstream end, it implies that the downstream end is 12 volts less than the reference. Okay, I think I've pretty much covered what I wanted to regarding rises and drops in polarity markers, but we've yet to discuss subscripts. We're going to quickly leave behind simplistic two-node circuits, and I'll help to establish some ground rules before we begin. If we're presented with a circuit with clearly named components, I can identify the voltage drop across a particular component with subscripts. If I wanted to know the voltage drop across resistor A, or the current through resistor A, I can say find VA or find IA. This level of detail breaks down if you've got nodes in there using the same identification scheme as your components. So we've got to establish some ground rules. Rule number 1, use different identification schemes for components and nodes. If components are letters, nodes are numbers, or vice versa. Rule number 2, voltage is a two-point measurement. If resistor A is hooked between node 1 and 2, I can say that the voltage drop across it is VA, or voltage at node 1 with respect to 2, or V12. In this case, V12 is equal to VA. The two subscript notation method is the most common means of identification and can be utilized at numerous points, even within the most complicated circuits. In our example on the right-hand side, consisting of 3 resistors in series, V23 is equal to the voltage drop across resistor B, or VB. V14 is equal to our voltage rise of E. If we know what comes up must come down, we should also realize that this two-point voltage measurement should mean the summation of the voltage drop across A, B, and C will equal our rise. We'll again return to this concept when we discuss Kirchhoff's voltage law. All I'm trying to do right now is get you used to double subscript notation. Again, double subscript notation is exceedingly handy because I can call for voltage measurements at numerous points with even the most complicated circuits. Here's a voltmeter measuring V12. Here's another voltmeter measuring V13, or the voltage at node 1 with reference to node 3. Okay, now that we've got an understanding of double subscript notation, let's introduce rule number 3. Rule number 3 utilizes previously agreed upon reference points. If you've established a previously agreed upon reference point, such as ground, more on ground later, you can use single subscript notation to mean voltage at a specific point with respect to this previously agreed upon reference point. Let's say I replaced node 4 with a ground connection and renamed it node 0. I can now use single subscript notation to mean the voltage at specific points with respect to node 0. No sense in saying V20 if you can just say V2, with the understanding that V2 is referenced from this common 0 node. This is kind of just like double subscript notation, where the second number is just not written because they're all referenced from the same node. This would be V1 using single subscript notation, or V10 using double subscript notation. And realizing our source is hooked between those same two nodes, we realize V10 should equal our supply voltage. This voltmeter is measuring V3 using single subscript notation, V30 using double subscript notation, and since it's measuring the voltage drop across a single component, namely component C, we could also say that this is VC. Notice using single subscript notation, however, the reference lead never left our commonly agreed upon reference, in this case ground. Finally, Rule 4. Rule 4 is kind of just a clarification of Rule 2 and 3 and probably means nothing to you at this point in your studies because we're kind of dealing with just one component right now. Realize voltage is additive or subtractive in nature, and when we progress through a loop, all our rises will equal all our drops. What goes up must come down. Again, we'll deal extensively with this in the Kirchhoff's voltage law lecture when we cover series DC circuits. But realize if we've got a common reference point in our circuit, let's say node 0, we could say V12 is equal to V1 with respect to 0 minus V2 with respect to 0. Utilizing a previously agreed upon reference point like ground kind of links our double and single subscript notation methods, where again V12 is equal to V1 minus V2. Okay, I think we've laid all our ground rules out regarding voltage rises and drops, polarity, and subscript and nodal notation. Let's try a couple reps of Ohm's law and see if you can follow along. Pause the lecture and see if you can determine the unknown quantity given the two known quantities. Visualize where instruments like ammeters and voltmeters would be placed in your circuit to measure these values. And additionally, see if you can use polarity markers to determine the direction of conventional current flow and vice versa. Use the pyramid representation of Ohm's law to help you out. Yes, for a couple of them, you will need to apply your knowledge of the 4-band resistor color code. If you don't know the 4-band resistor color code, check out the resistor color code lecture available at the Big Bad Tech channel before attempting these problems. Here's our first example. It's a 27.5 volt voltage source supplying current to a resistor with a 4-band color code, brown, brown, red, gold. Determine the magnitude and direction of current flow through this resistor. Do not just sit there and wait for me to guide you through these illustrated example problems. Pause the lecture, take out your paper, pencil, and scientific calculator and take your best shot. I hate to break it to you, but you can't get ripped by just watching an exercise video. At some point, you're going to have to do squat thrusts till you're stifling the urge to hurl. Even if you do hurl, I help you clean yourself up and walk you through the example problems after you've attempted them. Go ahead and take your best shot. A resistor with a 4-band color code of brown, brown, red, gold is a 1 for the first digit, 1 for the second digit, and it's followed by 2 zeros. In this case, it's a 1.1 kilo ohm resistor and has a plus or minus 5% tolerance as indicated by the gold band. We're just going to go ahead and assume that this is its nominal or nameplate value at 1.1 kilo ohms. What is the current through a 1.1 kilo ohm resistor when there is 27.5 volts across it? To solve for current, cover it up. Voltage is over resistance. Therefore, current, our effect, should be equal to voltage, our cause, divided by resistance, our opposition, or 27.5 divided by 1.1K, yielding us a current of 25 milliamperes. In this case, conventional current would leave our positive terminal of our source and return to the negative terminal. What is the polarity of the voltage drop across our 1.1 kilo ohm resistor? In this case, conventional current would enter our positive node and leave our negative node. Consider, however, this minor modification to this circuit. All I've done is I've flipped the voltage source upside down. In this case, it is still a differential of 27.5 volts. It is still a 1.1 kilo ohm resistor, and we would still expect to see an induced current of 25 milliamperes travel through our 1.1 kilo ohm resistor. The only difference that occurs is the direction of induced current. In this case, conventional current still leaves the positive terminal of our voltage source and returns to the negative terminal. Therefore, the polarity of the voltage drop across the 1.1 kilo ohm resistor is reversed because the direction of conventional current through it has been reversed. For all intents and purposes, this is the exact same circuit, and we have done nothing to change it other than flipping it on its head. What if I was to return to my initial upright orientation of my voltage source and added a reference node like ground? The addition of this reference node means nothing. There is still a differential of 27.5 volts across this 1.1 kilo ohm resistor. The only thing that's different is the fact that this 27.5 volts is now higher than a previously agreed upon reference point. In this case, 25 milliamperes will still flow from the positive terminal of our supply to the negative terminal and induce a voltage drop plus to minus across a 1.1 kilo ohm resistor. Consider another modification of this circuit, where a reference like ground is placed not at the negative terminal of our voltage source, but rather at the positive terminal. In this case, there is still a 27.5 voltage differential across our 1.1 kilo ohm resistor. And conventional current will still flow from the positive terminal of our voltage source to the negative terminal or voltage source and still induce a voltage drop across our 1.1 kilo ohm resistor with the indicated polarity. Again, ground means nothing. It is just a handy reference. In this case, our negative terminal is now 27.5 volts lower than what our reference is. There still exists a 27.5 volt differential across the 1.1 kilo ohm resistor, and you guessed it, 25 milliamperes of current will still flow through it. Example 2. An ammeter indicates 46.2 milliamperes of current is flowing through a 390 ohm resistor. What is the magnitude of the supply voltage? Ohm's law states that the voltage is equal to the current times the resistance. 46.2 milliamperes times 390 ohms yields roughly 18 volts. Example problem 3. How much resistance would you need to limit the current to 24 milliamperes if the supply voltage was 3 volts? Ohm's law states that resistance is equal to voltage divided by current. 3 volts divided by 24 milliamperes yields 125 ohms. Example problem 4. What would the voltage drop be across a resistor with a 4-band color code, blue, red, brown, gold, with an ammeter indicating 40 milliamperes of current is traveling through it in this direction? A blue is a 6, red is a 2, brown means it's followed by 1 0. The 4th gold band indicates it's a plus or minus 5% resistor, and we'll go ahead and just assume that this is its nominal value of 620 ohms. We're asked to find the voltage drop across this resistor, where conventional current enters the positive and leaves the negative. Ohm's law states that the voltage drop across a resistor is the current through it times its resistance. 40 milliamperes times 620 ohms yields 24.8 volts. Example problem 5. What is the 4-band color code of a resistor with a 20 volt drop across it and 35.7 milliamperes of current traveling through it? Ohm's law states that the resistance is equal to the voltage across it divided by the current through it, or 20 volts divided by 35.7 milliamperes, yielding approximately 560 ohms of resistance. This is not the answer to our question, however, because we're asked to find the 4-band color code of this resistor. A 5 is a green, a 6 is a blue, brown indicates it's followed by 1 0, and we'll assume it's a plus or minus 5% tolerance resistor with a gold 4th band. 6th example problem. What is the current supplied to a toaster with 19.2 ohms of resistance when it is supplied by a 120 volt source? Ohm's law states that current is equal to voltage divided by resistance, or 120 volts divided by 19.2 ohms, yielding a 6.25 amps of current. 7th problem. What is the resistance of a heater that draws 12.5 amps of current when it is supplied by 120 volts? Ohm's law states that resistance is equal to voltage divided by current. 120 volts divided by 12.5 amps yields 9.6 ohms of resistance. Finally, what is the current supplied by a 12 volt battery at starting when the starter motor has 80 milliohms of resistance? Ohm's law states that current is equal to the voltage divided by resistance. 12 volts divided by 80 milliohms yields 150 amps of current. This is not unusual. Such a large current draw is not sustained, but is rather a brief and intense occurrence. Alright, hopefully you did well in that first set of Ohm's Law reps. If you're in for the long haul and are committed to following the entire basic electronics series, DC through AC, all the way to 3-phase AC, this lecture serves as a great self-assessment check-in. You simply cannot proceed further without an understanding of Ohm's Law. Ohm's Law will be applied daily, and you must have this concept mastered. By all means, revisit the first part of this lecture and attempt the example problems again. I need you tracking with Ohm's Law, or this series is going to leave you quickly far, far behind. Alright, now that I've scared you straight or scared you off, let's talk about application of Ohm's Law to real-world situations, notably troubleshooting. Troubleshooting is a $1 million buzzword for an aspiring technician. Troubleshooting is the systematic identification of a problem exhibited by a system and subsequent correction. There exists a population of hucksters out there that try to sell troubleshooting as a mystical skill complete with magic charts, entirely separate from basic electrical knowledge. But they are all charlatans, frauds, and swindlers. Anything packaged and sold as troubleshooting without incorporating a thorough understanding of basic electrical properties is mere button pushing, totally inapplicable to real-world problems where what can go wrong often does. If you are enrolled in a hardware lab that accompanies your basic electronics course, you are troubleshooting, even if it doesn't say troubleshooting lab in the course description. I know it's frustrating when your lab instructor says, build me this, show me that, and things don't work out the first or the second or even the third time. But guess what? All that time you're spending fixing mistakes isn't wasted. It's being spent developing troubleshooting techniques. That's the point of a hardware lab. Get inside one and make mistakes in a safe and supportive learning environment. Make all the mistakes you possibly can and make them early and make them often. Make all the mistakes. Get them all out of the way up front. Here's the tricky part though. Be sufficiently aware enough to prevent their reoccurrence. Recognize the clues that led you to discovering the mistakes, learn from your mistakes, and never repeat them again. Troubleshooting is not a skill separate from basic electrical knowledge. At its most essential level, troubleshooting is the systematic application of basic electrical laws. Think of the term law. Ordinarily, we think of laws as things you get sent to jail for or pay a fine if you violate them. Ohm's Law is not that type of law. There is no Ohm's jail, and you can't pay some lawyer to twist the wording of Ohm's Law to make your circuit work like your lab instructor wants it to. Ohm's Law is a law like gravity, in that it goes to work every second of every day and cannot be disobeyed. Reality always obeys Ohm's Law, and it's your job as a troubleshooter to interpret reality. Say, for example, you're being tasked with troubleshooting a system that has an annoying tendency to burst into flames. Fire is a pretty good indication that the ampacity or current carrying capability of this device has been exceeded. Even if you have never seen this system before, nor have even the slightest idea what it does, as an effective troubleshooter understanding Ohm's Law, you are aware of two possible causes for this problem. If the current is too high, either the voltage is too high, or the resistance is too low, or maybe both. There are no other possible explanations for this occurrence. You don't need a flowchart to tell you this, and it's not like Ohm's Law is some magic secret. At its heart, your understanding of Ohm's Law quickly and efficiently cuts out a whole lot of dead ends and useless busywork. Determining why the voltage is too high, the resistance is too low, or both, is the next step in troubleshooting. This is where an intimate understanding of how a system is intended to operate comes into play. It is my intention with this series to provide you with sufficient technical knowledge to understand and troubleshoot any system you may run across. This is not some paint-by-numbers, quick and easy scheme where you can send some dude in the back of a comic book $50 and he'll send you a black belt in Kung Fu. This is going to be a long, hard, and grueling road. You'll look back at one day in a montage of memorable images accompanied by your favorite inspirational tune. The point is, skills like Ohm's Law are basic principles equivalent to learning how to block, kick, and punch, and they need to be practiced and developed up front. Sure, your $50 black belt might look cool, but when you're on your back getting ground pounded, it's not serving any purpose besides a convenient towel to clean you up with afterwards. Regarding the efficient and timely identification of problems within a system, realize the undesirable symptoms might have many possible causes, and quick diagnosis of the issue and subsequent correction is what identifies a technician as a good troubleshooter. In short, good troubleshooting is the combination of solid technical understanding of properties like Ohm's Law with good, organized, and efficient work practices. Recall from the efficiency lecture, available at the Big Bad Tech channel, where I introduced the concept of linked subsystems forming a larger system. Each substage's output feeds another substage's input. This same visualization can often be used to efficiently troubleshoot a malfunctioning system. If the end stage of a multi-stage system is not delivering a required output, where one starts troubleshooting is of critical importance. One might be led to believe that you have to start from the beginning and work all the way to the end, or vice versa, observing and recording all the way. This might work, but it is not the best use of your time. Troubleshooting is about the application of laws, but it's also about the application of these laws in a strategic manner. Don't waste time investigating functional areas of a system. Get to the trouble quickly and lay down the law. The best way to start troubleshooting a system composed of smaller subsystems is in the middle. If the middle stage is receiving its required inputs and delivering its required outputs, the problem is not upstream, it's downstream. One might jump to the next downstream stage, but again, this is not efficient use of your time. Jump to the middle of the remaining stages. If this substage is not receiving its required inputs, it obviously can't deliver its required outputs to the remaining stages. In this case, the problem is above stream of this current division. For more complex systems, you have to do several repetitions of this successive bracketing, and you will quickly and efficiently narrow down the target area to the source of the problem. Most likely, it's your lab partner. In these early troubleshooting examples, we'll be dealing with single elements inside simple circuits, and our system obviously has a limited number of stages. Though these initial troubleshooting scenarios may seem basic in nature, I'll introduce and you will find yourself dealing with troubleshooting scenarios of increasing difficulty. I'm bringing these high-level concepts to your attention early so you can start getting into this frame of mind now and develop good troubleshooting practices up front. Let's say we're supplying 20 volts to a 1 kilo ohm resistor. Do the calculations first. What's the current you'd expect flowing through this resistor? Ohm's law states that current is equal to the voltage across it divided by the resistance. 20 volts divided by 1 kilo ohm yields 20 milliamperes. Let's say though, as soon as you turn on the power, this 1 kilo ohm resistor's paint job turns an ugly shade of brown, starts smoking, and is quickly engulfed in flames. I know we haven't spent a lot of time on power calculations, but when something sets on fire, you can be sure you've probably exceeded the power rating, in this case because current was too high. What's the problem? If current is too high, it's because the voltage is too high or the resistance is too low. The answer is right in front of you if you know where to look. Your circuit has a power supply and a resistor, so it's obviously one of these two that are at fault. A quick check of your voltage source with your voltmeter indicates it's at 20 volts. What's the problem? It's your lab partner. I warned you about this, didn't I? Instead of grabbing you a 1 kilo ohm resistor with a brown, black, red, gold 4-band color code, he grabbed you one with a brown, black, black, gold color code. Pay attention to the third band. Didn't I say that before too? Pay attention to your lab partner. Never trust them. They're good for fetching snacks and parts, but verify everything they bring to you is either edible or usable before eating it or using it. A resistor with a brown, black, black, gold 4-band color code is a 1, 0, followed by 0 zeros, or 10 ohms of resistance. A 10 ohm resistor provides substantially less opposition to the same voltage source, 990 ohms less to be exact. In this case, our circuit would have 20 volts divided by 10 ohms, or 2 amps of current flowing through it. No wonder it burst into flames. Ohm's law says current will be high for low resistance paths. Tying this troubleshooting example to the development of good lab practices, had you taken the time to measure and record your observed resistance values, or at the very least double-checked your lazy lab partner's work prior to turning on the power, this whole sordid tale would never have happened. Your lab partner isn't there just to make you seem good-looking with reference to them, or go get you energy drinks and cigarettes from the vending machines. They're there to dummy check your work, and believe me, you are there to double and triple dummy check their dumb work. Do the calculations up front, and you'll know what to expect. Make sure you're using the correct components, connecting them in the correct manner, supplying them with a desired voltage, and taking measurements in the right place. Imagine how well lab will go if you know what you're doing. Let's try another simple troubleshooting example. Let's say we're observing no voltage drop across a 1 kilo ohm resistor hooked to a 20 volt source. This time it really is 1 kilo ohm, because no way are you going to fall for that one again. What's the problem? Lay down the law. If there is no voltage drop across a resistor, it means that there is no current through it. Ohm's law says so, and your ammeter would indicate so. Ordinarily, a 20 volt source would supply a 1 kilo ohm resistor with 20 milliamperes of current. If there's no current, 1K times 0 yields 0 volts. Did you turn the source on? You'd be surprised how many troubleshooting scenarios are resolved simply by pressing the large red switch that says on. I've done this myself more often than I'd like to admit. What if the source really was on and you still observe no voltage drop? In this case, again, there is no current through it. What is stopping the current? Perhaps something with an infinite resistance. I previously assured you that it was in fact a 1 kilo ohm resistor. However, is this really the only element in a circuit with your source? Or is there something else in series with it? Think about what I'm asking. What is something with an infinite resistance? Something with an infinite resistance is an open or an incomplete circuit. This is where intimate knowledge of your circuit building environment, typically a protoboard, comes into play. The source may be on, and the positive terminal may be connected to your ammeter input, and the ammeter output might be connected to one end of the resistor. But if the other end of the resistor is not connected to the negative terminal of the source, no circuit exists. The same thing could be said for an open between the positive terminal and our ammeter input or our ammeter output and the top terminal of our resistor. A complete path must exist for current to flow through this circuit. In either case, the 1 kilo ohm resistor is now in series with an infinite resistance. Ohm's law still applies. Current is equal to supply voltage divided by, in this case, total resistance. 20 volts divided by infinity plus 1 kilo ohm. Anything divided by infinity is 0. There's no current because there's no path for current. If there's no current flowing through our resistor, there's no voltage drop. Ohm's law says so. How can we use our ammeter and our basic knowledge of electrical quantities to figure out where the open exists? I know we haven't gone into details about voltmeters nor Kirchhoff's voltage law yet, but recall, for every rise there is an equal drop. If there is an open between one terminal of our resistor and the negative terminal of our power supply, across the open is where the voltage drop occurs. In this case, both terminals of the resistor are at the same potential as the positive terminal of our voltage supply, and the voltage differential between them is 0. If there is no differential across them, there is no current flow through them. This is like our tube and ball analogy laid flat on the top of a skyscraper. The ball won't roll because there's no differential. The same thing but different for an open between the power supply's positive terminal and the top end of our resistor. The voltage drop again occurs at the open, not across the resistor. Both terminals of the resistor are at the same voltage as the negative terminal of our voltage supply. If there is no voltage differential across these terminals, current will not flow through it. This is like the tube and ball analogy, where the tube is laid flat on the floor. The ball won't roll because there's no differential. Can you see how Ohm's law is the chicken before the egg, before the chicken, before the egg, and so on? Every single restatement of it just goes to further reinforce how Ohm's law is real and observable and very, very useful. I could do this all day, but I won't, because we've got a long way to go and a short time to get there. Consider a completely functional circuit. The 20 volt source really is 20 volts. The 1 kilo ohm resistor really is 1 kilo ohm, and it's really hooked in a complete circuit. Your lab partners are observing no voltage drop across the 1 kilo ohm resistor. What's the problem? It's your lab partner. They're using the voltmeter incorrectly. Voltage is a 2-point measurement. When you're measuring voltage with your reference and high lead at the same point, obviously there's no differential. Instrumentation errors are the most nefarious of errors, and largely the ones I hope to permanently abolish with a lab practices lecture accompanying this playlist. You simply must know how to use common instrumentation to take valid observations. Even if your circuit is functional, you can't get good readings if you're using your DMM incorrectly. Again, voltage is a 2-point measurement across something. If both leads are measuring the same point, there is no differential between them. Realize there is no way one can possibly foresee and anticipate all possible sources of problem with the system, and anyone who says so is a liar. I am not saying that technicians accustomed to troubleshooting by the company book or using established procedures can't resolve errors, but I am saying that a flexible technician with knowledge of basic electrical properties like Ohm's Law can resolve errors that aren't even in the book. That's the point of practicing a discipline like martial arts or electronics. Think beyond the first move. Allow yourself to swim through a million combos you've done a million times before. And even if you haven't, you have the skills to see patterns and recognize their resolution. That's the purpose of study. That's the purpose of practice. It's hard and exhausting for a reason. When some uppity dummy throws a front punch at you, or some switch doesn't work, you're just going to hit it like a hive of snakes striking 10 at a time. Problem solved. So simple. Lay down the law. Before we wrap up, let me give you some general troubleshooting advice for a lab environment in addition to the scenarios we already discussed. Again, my advice cannot possibly cover all possible scenarios, but in my opinion, it is sufficiently general enough to encompass some basic principles of troubleshooting for your first couple DC circuit labs. Short circuits mean 0 ohms of resistance. If there's 0 ohms of resistance, you bet there's going to be current, and it's going to be exceptionally high. Open circuits mean infinite resistance. With infinite resistance, no current can flow. If you can walk away from this series understanding just these two simple facts, I will consider my efforts having not gone in vain. If you can't remember both, remember one. Open circuits will not allow current to flow. If you turned all possible troubleshooting scenarios into animals, where their population is representative of their frequency of occurrence, the open circuit is like the beetle family, which even if you combined all other species on Earth, would still outnumber them like 1,000,000 to 1. Your first error is your dubious choice of lab partners. Your next 999 errors are going to be open circuits. Do the calculations first. Know what to expect. Double check the components. Make sure you're using the right ones. Read the values on the side. You could use supporting instrumentation like an ohm meter to measure resistance. Check to see if a switch works before you put it in a circuit. A closed switch is a short, or 0 ohms of resistance. An open switch is infinite ohms of resistance. Lab equipment gets hammered by generation after generation of students. Sometimes out of sheer exhaustion, components or meters just die. Double check the circuit. Make sure it's hooked up as intended. I know it seems dumb, but use colored wires. Number the nodes. Pretend your current flowing through the circuit. Visualize it. If this stupid trick works, it's not stupid. If you're using a protoboard as your circuit building environment, look at it from all angles, not just the top when you're troubleshooting connections. Different angles often quickly reveal a missed or off by one connection. Supply the circuit with the correct voltage. Use a voltmeter to make sure the power supply is set properly before you begin. Measure it again when it's hooked to your circuit. When we get to series circuits, I'll explain why this is necessary. I know there's an analog needle on the front of some power supplies, but they're inaccurate almost to the point of being useless. Use your DMM. If you're going to use your DMM, use it properly. We already covered the ohm meter in a previous lab practices lecture. We'll go into detail about voltmeters and ammeters real soon, but recall the basics: function, leads, range, and placement. Use the checklist. Ohm meters are never used on live circuits. They read the resistance from terminal to terminal with a device of interest removed from the circuit. Voltmeters read voltage across something. Voltage is a 2-point measurement. Ammeters read current through something. Current is a single-point measurement which must flow in and indoor and outdoor. Your circuit may be completely functional, but you might just be measuring it improperly. Improper use of a DMM might not just result in bad measurements, you might damage the meter, your circuit, or yourself. If you are absolutely certain your circuit is functional and it is still not conforming to your expectations, reanalyze your expectations. That's science, dudes. At any moment, I am prepared to abandon long-held convictions because rigorous and proven observations have demonstrated otherwise. Mankind no longer believes angry gods are the cause of thunder and disease because it's been proven that thunder and disease are caused by ghosts and aliens. Look it up. This is not to say that your circuit will ever disprove Ohm's law. I have yet to witness a lab group do this. I've on numerous occasions, however, observed students using something I call Mohs Law, the opposite of Ohm's Law. If the observations aren't jiving with your numbers and all else has failed, check your numbers. Finally, trust no one. Verify. There will come a time when you are working on a system that have a potential to injure or kill you. Your life is on the line. Check to make sure all sources of hazardous energy are locked out and tagged out prior to initiating work. Bad habits are hard to break. Start safe work practices now. Okay, that about wraps it up for the Introduction to Ohm's Law lecture. Do not for a moment think we've seen the last of this. Ohm's Law is something that we've applied in almost every illustrated example in the remainder of this playlist and all those others following. We've yet to graph Ohm's Law, which we'll do later in experimental verification videos, but start to think now of what different permutations of Ohm's Law would look like visually if you kept one value constant and varied another. Here's a hint, it's probably linear. Finally, here's one last visual on Ohm's Law I never grow tired of showing students. I think this should be a mandatory poster in every lab environment. It goes well accompanying a kitten clutching a branch that says, "Hang in there, buddy." In conclusion, this lecture took a close look at the most fundamental of all electrical relationships, known as Ohm's Law. We learned the cause, effect, and opposition relationship between voltage, current, and resistance, and used it to calculate unknown quantities given known or observed inputs. Additionally, we had a general introduction to troubleshooting basic electrical circuits using Ohm's Law. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.